Sensors 2010.10.1890-1917, DOI 10.3390/S1003-01890. Sensors ISSN 1424-822, www.mdpi.com/journal/sensor. Review: Electrical Capacitance Volume Tomography, Design and Applications. E. Wang, Qussai Marashdeh, Liang-Shih Fan, and Warsito. William G. Lowrie, Department of Chemical and Biomolecular Engineering, The Ohio State University. 40 West 19th Avenue, Columbus, OH 43210, USA. Emails: Wang Fef at chbemn.ohsu, FW, Marashdeh.1 at osu.edu, WW, Warsito at yahoo.com, www. Author to whom correspondence should be addressed. Email: fan at chbemn.ohsu. Tel +1 614 688 3262. Fax +1 614 292 3769. Received 15 January 2010. In revised form 10 February 2010. Accepted 28 February 2010. Published 9 March 2010. Abstract: This article reports recent advances and progress in the field of electrical capacitance volume tomography, ECVT, developed from the two-dimensional electrical capacitance tomography, is a promising non-intrusive imaging technology that can provide real-time three-dimensional images of the sensing domain. Images are reconstructed from capacitance measurements acquired by electrodes placed on the outside boundary of the testing vessel. In this article, a review of progress on capacitance sensor design and applications to multi-phase flows is presented. The sensor shape, electrode configuration, and the number of electrodes that comprise three key elements of three-dimensional capacitance sensors are illustrated. The article also highlights applications of ECVT sensors on vessels of various sizes from 1 to 60 inches with complex geometries. Case studies are used to show the capability and validity of ECVT. The studies provide qualitative and quantitative real-time three-dimensional information of the measuring domain under study. Advantages of ECVT render it a favorable tool to be utilized for industrial applications and fundamental multi-phase flow research. Keywords: electrical capacitance volume tomography, ECT, ECVT, capacitance sensor, multi-phase flow, non-intrusive testing, process imaging. Open access. NSORS 2010-10, 189. Introduction. Industries such as pharmaceuticals, food, and petrochemicals employ multi-phase flows in the processes. Phases in such processes include gas-solid, gas-liquid, and gas-liquid-solid 1-6. An insight to phase interactions is essential to the understanding of the operation of multi-phase flows. Such sight is provided by different measurement techniques with quantitative local and global dynamic formation of the flow that is useful for system design and control. The area of multi-phase flow measurements has been an intensive research topic for several decades. Accurate multi-phase flow measurement technologies present practical challenges, and continued progress is being made towards improving these technologies. Simple and low-cost intrusive probes have been used in many operation systems to obtain flow information 7 to 16. They require some penetration in the process's flow field for signal acquisition. But such an invasive procedure may interrupt the local physical flow behavior of the flow and affect the accuracy of the measurements. The need for a more accurate measurement technology led to the development of process tomography, a measurement technology that provides cross-sectional images of phase concentrations 17-18. Process tomography becomes even more appealing when non-intrusive sensors are used to obtain the cross-sectional images. Applications of such process imaging technologies have been gaining momentum over the past several years. Examples include magnetic resonance imaging, MRI, positron emission tomography, PET, X-ray tomography, gamma-ray tomography, GRT, electrical magnetic tomography, EMT, and electrical capacitance tomography, ECT, 19-40. Those tomography techniques mainly differ in the sensors used and signal obtained to form an image. A particular tomography technology is favored over another for certain application based on cost, acquisition speed, image reconstruction speed, safety, simplicity, resolution, applicability to vessels with complex geometries and different sizes, 3D capability, and the nature of the processes under investigation. ECT is among the most favored tomography technologies in terms of cost, speed, safety, applicability to vessels of various sizes and geometries, and simplicity. With the recent introduction of volume technology, ECVT, capacitance sensors can now be used for real-time 3D volume imaging, 4142. Capacitance volume tomography is based on reconstructing a 3D image from a capacitance signal obtained from a 3D capacitance sensor, 42. ECVT utilizes the nonlinearity in electric field distribution to track changes in phase distributions. ECT was first introduced in the 1980s by a group of researchers from the U.S. Department of Energy Morgantown Energy Technology Center, METC, to measure a fluidized bed system, 4344. Subsequently, this technology was applied to measure oil concentrations and pneumatic conveyors by a research group led by Maurice Beck at the University of Manchester Institute of Science and Technology, UMIST, during the 1990s, 1832, 45, 47. ECT was also applied to image pharmaceutical, fluidized bed dryers, and three-phase chemical engineering reactors in this same decade, 31, 48, 50. Solids pneumatic conveying systems and oil pipelines, the cross-sectional components hold-up distributions are usually obtained from ECT to monitor the flow conditions inside transport vessels, 51-52. In fluidized bed reactors, the gas-solid, gas-liquid-solid hold-up, and bubble-size distributions are obtained by ECT for basic multiphase flow science, reactor design, and operation. L 6, 34, 35, 38, 40, 58. ECT, coal, bite, PET, cis, phase, P, DUF, DIF. Sensors 2010, 10. 189. The main limitation of ECT technology is in the inadequate spatial resolution it can provide. The measurement resolution is dependent on ECT sensor designs and image reconstruction. The resolution of ECT images can be improved by increasing the number of sensors. However, the highly nonlinear reconstruction problem is still considered the main obstacle to increasing resolution. This problem is even more evident in the ECVT volume technology as the nonlinearity of the problem is increased substantially. ECVT emerged about 5 years ago from the labs of The Ohio State University. Researchers from the Technical University of Lodz and the University of Manchester recently developed a 3D electrical capacitance tomography for 3D visualization. 5960. The resolution is expected to improve as research in ECVT gains increased attention, 36, 37, 41, 42, 61, 62. Despite the solution limitation, ECVT leads other imaging technologies in terms of real-time 3D feature, applicability to complex geometries, reduced cost, and low-profile sensors. In this review, ECVT will be presented in the context of three-dimensional sensors with different sensor configurations, size, and geometries. Several case studies are illustrated to demonstrate the potential usefulness of applying ECVT for imaging multi-phase flow systems. All the capacitance measurements reported in this study were obtained using the PTL charge-discharge 12-channel acquisition hardware, with the exception of the images given in figures 10 and 11b, where the Edward Technology AC-based hardware was used. Principle of ECVT. ECVT technology is based on utilizing nonlinear distributions of electric field lines to reconstruct a volume image of different materials in the imaging domain. The low profile and flexibility of capacitance sensors, increased number of imaging frames per second, and relatively low cost of the ECVT system are characteristics that have moved the technology to the top of the list of industrial imaging tools. This step forward is a continuation to developments in capacitance tomography, technology that was introduced by the U.S. Department of Energy in the 1980s. Figure 1 is a sketch of an ECVT system. Figure 1. Sketch of an ECVT system. Sensors 2010, 10, 189. It consists of an ECVT sensor, data acquisition system, and computer for data recording and image construction. ECVT measures capacitances between all electrode pairs of the ECVT sensor, with C channels, which gives a total n(n-1) over 2 independent capacitance measurements. The measurements represent a set of normalized independent capacitances from the sensor. 1. Operating principle. Similar to other tomography techniques, capacitance tomography in both its 2D and 3D forms is based on reconstructing a physical property from a set of boundary measurements. For capacitance tomography, the physical property is dielectric constant distribution in the imaging domain, and the boundary measurement is electric capacitance. Capacitance tomography belongs to the soft field category of tomography techniques, where electric field lines are non-linearly related to dielectric constant distributions. This non-linear relation introduces a higher level of complexity that requires powerful reconstruction algorithms, which are discussed in the next section. Electrical capacitance is related to dielectric, permittivity, constant distribution. The electric potential and permittivity distributions are described by the Poisson equation. E pi z u x equals negative epsilon p u x pi z, where epsilon and phi represent the dielectric constant, permittivity, distribution, and the potential distribution, respectively. In capacitance volume tomography, sensors can be designed to fit any physical geometry. However, this flexibility further complicates electric field distribution, resulting in an uneven distribution of solution in the final reconstructed image. This problem can only be addressed by employing advanced image reconstruction techniques that consider the sensor design for maximizing image resolution. Different approaches for image reconstruction are discussed in the following section. However, the field of image reconstruction is still open for further improvements. 2. Reconstruction. The nonlinear nature of electric field distributions from capacitance sensors has been the main challenge to the technology resolution for both 2D and 3D volume imaging. Two main reconstruction approaches have been employed to address this problem: linear projection and optimization. In the former, the capacitance measurements are iteratively projected through a linearized sensor matrix, yielding a concentration image representative of different phase distributions. In the latter, a set of predefined measures are optimized iteratively to yield the most probable image for a set of measurements. Iterative linear reconstruction is simple to implement and requires less computational power. However, it is bounded by its low resolution, introduced image artifacts, and lack of reliable quantitative image representation. The converse, optimization reconstruction, is more complex to implement and requires more computational power. Optimization reconstruction provides better image resolution and less image artifacts, and it is more suitable for applications where quantitative information of the flow under investigation is required. These features become more. Sensors 2010, 10, 1891, DNN-MOIRT are considered superior relative to other reconstruction methods 2938. The optimization algorithm optimizes 4 objective functions related to the measured capacitances and constructed image. The 4 objective functions are characterized by the mean square error between forward solution of reconstructed image and capacitance data, the smoothness of reconstructed image, entropy of reconstructed image, and the 3D-2D matching function of reconstructed image. Optimization of the 4 objective functions is implemented using the Hopfield neural networks. The advantage of using the Hopfield neural networks for optimizing the final reconstructed image is that it preserves a monotonic decreasing error function as iterations proceed. Optimization reconstruction has also the advantage of optimizing functions related to both the measured capacitance and final image. This advantage is a major improvement for eliminating noise and artifacts from the final image. The Hopfield neural network technique does not require training or prior knowledge of the flow. As constructed images reported in this paper were obtained using the 3D NN-MoIRT reconstruction algorithm. Further details of the reconstruction technique are provided in Warsito et al. Table provides a summary of the 3 major types of image reconstruction techniques for electric capacitance tomography. Table 1. Key techniques used in solving the inverse problem of capacitance tomography. Reconstruction method. Methodology. Characteristics. Example: single step, linear. The sensor system is linearized usually by constructing a sensitivity matrix. The image is obtained by back projecting the capacitance vector using the sensitivity matrix. Fast, low image resolution, and introducing image artifacts. LBP 33. Iterative linear back projection. The mean square error between the capacitance data and forward solution of the final image is minimized by iterative linear projections using the sensitivity matrix. Slower than single-step linear, providing better images than single-step. 33. Landweber ILBP. Optimization. A set of objective functions are minimized iteratively to provide the most likely image. Different optimization algorithms and objective functions can be used. Slower than iterative linear back projection, providing better images than iterative linear back projection. 42. 3D NN-MoIRT 42. Sensors 2010-10. 189. Potential applications. Applications of ECVT include current applications of capacitance tomography, in addition to new applications introduced by ECVT flexible sensor design. Capacitance sensors have also been used to image gas, liquid, and solid multi-phase flow systems. They have also been used to image reactors of different sizes, extending from micro-level columns up to columns of 60 inches in diameter. 63. Capacitance sensors have also been demonstrated to image flames and combustion. 64. In the following part of this review, examples of regular and irregularly shaped sensor are used to demonstrate the feasibility of the technology for imaging regions previously considered inaccessible. ECVT sensors. The sensor shape, configurations, and channel number play an important role both for the 2-dimensional ECT and 3-dimensional ECVT measurements. Based on the reconstructed image, capacitance sensors are classified into 2-dimensional ECT sensors and 3-dimensional ECVT sensors. Figure 2 shows the configuration of a 2-dimensional ECT sensor. Figure 2. 2-layer ECT sensor configuration. It contains 2 layers, and each layer has 12 channels. The 2 layers are independent, and the 2-dimensional filed variation in radial directions is realized by measuring the capacitance between a pair of electrodes in the same layer. There are M-1 times 2 combinations of capacitance measurements at layer, where M is the number of electrodes in the layer. The length of the ECT sensor in the axial direction is assumed to be infinite here. However, the length of the electrodes in the actual sensor is limited by the sensor dimensions, which is based on practical limitations, leading to what is known as the fringe effect. This effect is translated as artifacts in the final image. 42-65. The permittivity distribution in each test plane is obtained by reconstructing the image from capacitances in the same plane. The permittivity is related to the concentrations of phases, and, as a result, the concentration distribution of the multiphase flow in the cross-sectional area of the testing vessel is visualized. Sensors 2010-10. 189. E-dynamic multiphase flow behaviors in the testing vessels. A quasi-3D image is a series of 2-dimensional images stacked along the z-axis of the vessel in the time sequence in which the images are captured. Du et al. 35 use the quasi-3D images constructed from a series of images over a period of time to capture the bubble size and shape in the gas-solid fluidized bed. 2-dimensional ECT sensors have been studied intensively in the past several decades. 31. Most previous ECT studies, the fringe effect was ignored or accounted for as a deviation from the ideal response in an ECT sensor. With the introduction of ECVT, the nonlinear distribution of the electric field is utilized for 3D imaging, and ECVT sensors are designed based on this idea. Field variations in both radial and axial directions are considered for proper ECVT sensor design. A relatively identical distribution of the electrical field in all three dimensions is required for high-quality sensor design and high image resolution. The sensor shape, electrode configurations, and the number of the electrodes are three key elements in three-dimensional ECVT sensor design. Designs of ECVT sensors on vessels with complex geometries and variable sizes are desired in many industrial processes. The multi-phase process under investigation is the basis for determining a desired sensor design. 1. Cylindrical shape sensor. Straight vessels, such as fluidized bed reactors, solids pneumatic conveying systems, oil transport pipes, and liquid or gas storage tanks are widely used in industry. 6. Cylindrical shape ECVT sensors for such vessels are very common due to their regular shape and potential applications in straight vessels. Sensors with multiple layers and rectangular electrodes are typical for cylindrical shape vessels. A variation in the number of layers and plate shape provides control over increasing or decreasing axial resolution with respect to spatial resolution. Figure 3 depicts three different sensor designs for a cylindrical multi-phase flow section. Figure 3A is a typical cylindrical shape ECVT sensor. It has 3 layers and 4 identical rectangular electrodes in each layer. The electrodes in each layer are shifted 45 degrees with respect to electrodes in adjacent layers. This shift enhances the resolution of the reconstructed image as evidenced by the measurements. The shift is illustrated in Figure 3A. The axial and radial resolution increases as a function of the number of layers and the number of electrodes in each layer. For a fixed number of electrodes, the increase of layers is counteracted by a decrease in radial resolution. Varying the electrode shape also plays a role in this resolution trade-off. A limitation on the maximum number of layers that can be used is usually introduced by the data acquisition and operation. The signal-to-noise ratio for a pair of plates decreases as the separation between plates increases. For applications with limited space in the axial direction, 3D features of ECVT sensors are introduced by changing the shape of the plates rather than increasing the number of layers. Figures 3B and 3C are some examples of two-layer and single-layer sensors, respectively. The two-layer ECVT sensor illustrated in Figure 3B appears to be similar to the two-layer or twin-plane ECT sensor in Figure 2. The difference between them is that the capacitance measurements are also recorded for plates within the same layer and across the layers for the ECVT sensor, whereas the two layers are independent during measurements for the ECT sensor. A useful method to qualitatively assess the quality of the sensor design is to view sensitive regions between each pair of plates. This is accomplished by first forming the sensitivity matrix of the sensor or solving the forward problem. Sensors 2010, 10. 189. Figure 3. Configuration of ECVT sensor. A. 3-layer sensor. B. 2-layer sensor. C. Single-layer sensor. A. B. C. A major advantage of ECVT sensors is that they can be applied to vessels of various sizes. Figure shows an example of sensors with different diameters. A sensor for an upscale unit constructed to image a flow in a 60-inch ID vessel is depicted in Figure 5. A triple-layer sensor design may cause radial accuracy problems due to the small length-diameter ratio for the sensing domain of such a 60-inch ID. Sensors 2010, 10, 189. Suitable for the measurements. Each capacitance electrode has an inherent 3D characteristic in its design. Figure 5-B is a photo of the industrial reactor and the 60N ECVT sensor applied on such a system, respectively. The sensor successfully imaged gas-liquid flow in the unit when the unit was running. Figure 5-C shows the liquid concentration in the unit obtained by the 60N ECVT sensor. Figure 4. Photos of ECVT sensors with different diameters. A. 1N ID. B. 2N ID. C. 4N ID. D. 12N ID. A. B. C. D. Figure 5. 60N ECVT sensor. A. Sensor configuration. B. Photo of the 60N sensor. C. Liquid concentration in the unit. Sensors 2010, 189. Figure 5 Cont. B. C. The flexibility of ECVT sensor design is also demonstrated in the modified sensor in Figure 6. In this figure, an ECVT sensor has been successfully applied to visualize instantaneous flow behaviors of a horizontal gas jet into a gas-solid fluidized bed. 6266. The horizontal gas nozzle is on the wall of the fluidized bed reactor and penetrates the ECVT sensor device. Figures 6A and B are the sense design and actual setup of the ECVT sensor modified to accommodate the horizontal jet, respectively. Figure 6. ECVT sensor for the visualization of horizontal gas jet penetration in a gas-solid fluidized bed. A. Configuration of the sensor with a jet tube. B. Photo of the ECVT sensor. Sensors 2010. 10. 190. Figure 6. Continue. B. The sensor consists of 12 rectangular electrodes with 3 layers of capacitance electrodes and 4 electrodes in each layer. The edges of 2 adjacent plates in the middle layer of the sensor are modified to fit a horizontal gas tube into the fluidized bed. 2. Sensors with complex geometries. Vessels with complex geometries are very common in engineering processes. For example, T-shape and bends are used to change the flow directions in solids pneumatic conveying systems. T-shape, V-shape, and bends are applied at the inlet and outlet parts in most gas-solid circulating fluidized bed reactors, respectively. The funnel shape is found in the expansion/contraction section of vessels or in reverse flow cyclones. Flexible ECVT sensors are able to image flows in such geometries by changing the plate shapes to fit the intended geometry. Figure 7, A to D, shows some ECVT sensor configurations for the smooth right-angle bend, sharp right-angle bend, T-shaped vessel, and a half-cylindrical vessel. Figure 7. Configurations of ECVT sensors. A. Smooth right-angle bend. B. Sharp right-angle bend. C. T-shaped vessel. D. Half-cylindrical vessel. Answers 2010. 10. Sensors 2010, 10. Sensors 2010, 10. Sensors 2010, 10. 190. Figure 9 content. C. 3. Sensor channel number. The number of capacitance sensor channels can significantly affect the capacitance measurement. Increasing the channel number is expected to increase the quality of the images. However, the number of channels is restricted by hardware limitations related to decreased signal-to-noise ratio. An online ECVT system has been successfully demonstrated at The Ohio State University. Figure 10A shows a photo of an 8-channel online ECVT sensor. It has 2 layers with 4 electrodes on each layer. The acquisition box is connected to the laptop by a USB cable. Tap water is used as the fluid media in the container. The online images of the water movement in the container and the fluctuation of the water-free surface are obtained instantaneously by the ECVT system, illustrated in Figure 10B. Figure 10, 8-channel online ECVT system. A. Photo of the 8-channel sensor. B. Online water surface measurement using the sensor. Sensors 2010, 10. 190. Figure 11. Cont. B. 12-channel and 32-channel ECVT sensors, illustrated in Figures 11A and B, were all developed at The Ohio State University. Figure 11. ECVT sensors with multiple channels. A. 12-channel sensor. B. 32-channel sensor. Different elements of the ECVT system and their effect on the overall operation of the system have yet to be investigated. Increasing the number of electrodes, changing the plate shape, modifying the sensor design, or revising available imagery construction techniques are all examples of possible developments. Computer simulations are used to design and validate ECVT sensors. 65. They can simulate the capacitance measurements before the fabrication of the real sensor. The ECVT sensor design is important to the determination of the image resolution and accuracy. Table 2, several sensor designs are compared based on sensor symmetry, axial resolution, and radial resolution. 3 scales, i.e., high, moderate, and low, are used to describe the quality of the measurement. Sensors 2010, 190. Table 2, comparison of different sensor geometries in terms of symmetry, axial resolution, and radial resolution. Sensor type, sensor symmetry, axial resolution, radial resolution. Cylindrical sensor, with 1 layer, high. Low, sensitivity decreases toward center. High, sensitivity decreases toward center. Cylindrical sensor, with 2 shifted layers. Moderate. Moderate, sensitivity decreases toward center. Cylindrical sensor, with 3 shifted layers. Moderate. High, sensitivity decreases toward center. Moderate, sensitivity decreases toward center. Planar sensor with shifted planes. Moderate. Low, sensitivity decreases away from sensor. High, sensitivity decreases away from sensor. Sense sensor. Low, depends on sensor plate arrangement. Depends on sensor plate arrangement. Applications. ECVT has been successfully applied for measurements of multi-phase flow systems. Measurements are provided in real time for local or global 3-dimensional components of multi-phase reactor. The technology has been applied to gas-solid fluidized bed, gas-liquid, and gas-liquid solid bubble columns, gas-solid circulating fluidized beds, and multi-phase flows in vessels with complex geometries. Examples here include imaging of the choking phenomenon, described as a sudden change of dilute solids flow to a slugging flow in the vessel. 54. The experiment took place in a 0.1 meter ID gas-solid fluidized bed, and a 3-layer 12-channel cylindrical 3D ECVT sensor was used. The sensor configuration is described in Figure 3A. Real-time solids holdup in the riser of the circulating liquidized bed during the choking transition was reported using both a 2D ECT sensor and a 3D ECE sensor. 54. In another example, Warsito and Fan, 41, studied the dynamics of spiral bubble motion in a gas-liquid bubble column with air and Norpar 15 as the gas and liquid phases respectively. In the experiment, ECVT was used for the measurement of 3D gas and liquid holdups and the dynamic motion of bubble plumes in the bubble columns. ECVT was also used for imaging non-uniform geometries as reported by Wang et al. 6266. Their work studied the horizontal gas jet penetration in a 12-inch gas-solid fluidized bed using a modified cylindrical ECVT sensor. The configuration and resolution photo are illustrated in Figure 6A and 6B. The sensor was used to image instantaneous three-dimensional jet shape as well as developments in the gas-solid fluidized bed. The maximum penetration length and width of the horizontal jet and the coalescence of the horizontal jet with a bubble rising in the fluidized bed were qualitatively and quantitatively investigated using ECVT. NASA, Tech for Imaging LLC, and National Institute of Standards and Technology are collaborating on a project to use ECVT technology for measurements of a cryogenic fuel gauge in a zero-gravity environment. The technology will be assessed for applications for missions in space. 68. ECVT 2010, 10. 190 pressure transducer, X-ray tomography, magnetic resonance imaging, MRI, and ECT. 2265. Holland et al. 22 quantitatively compared the flow dynamics in a 2-inch ID gas-solid fluidized bed using MR and ECVT. The average solids holdup, the solids holdup distribution, dynamic bubble shape, motion, and bubble frequency on the same system were both obtained from MRI and ECVT. The results from the two techniques were found to be in good agreement. The fast imaging speed of ECVT also enables the use of 3D images to estimate average voxel velocity. 6972. As a demonstration of ECVT accuracy, a conical cavity in a plexiglass cylinder was imaged moving in a 0.1 meter ID vessel as depicted in Figure 12. The OD and height of the cylindrical object was 10 centimeters and 13.5 centimeters respectively. The ECVT sensor was mounted on the periphery of the vessel. The sensing domain was a cylindrical volume with a diameter of 10 centimeters and a height of 12.5 centimeters. 3D NN Moyar was used for the image reconstruction with a resolution of 20 × 20 × 20 for the reconstructed image. The acquisition speed was 80 Hz. The phase concentration, plexiglass, was calculated from the E-permittivity distribution in the sensing domain based on the capacitance measurements from the wall of the vessel. Figure 13 shows the three-dimensional dynamic view per two frames of the cylindrical object moving downward in the vessel. In each sub-image, the left images are snapshots of the X-plane and half top and bottom XY planes, whereas the right images are snapshots of top, middle, and bottom XY planes of the sensing domain. X, Y, two horizontal directions, Z, vertical direction. The red and blue colors represent high and low phase concentrations, plexiglass and air, respectively. The liner conical shape surface, the out cylindrical shape surface, and the dynamic positions of the object are clearly illustrated by the three-dimensional images. The results show the capability of ECVT technology to provide real-time, three-dimensional images of complex solid objects in the sensing domain, which can be extended to object detection and monitoring in industrial processes. Figure 12. Sketch of a plexiglass cylinder with a conical cavity moving in a cylindrical ECVT sensor. NSORS 2010, 10. 190. Figure 13. Three-dimensional dynamic view of the cylindrical object moving in the vessel from ECVT. T equals 0.00. T equals 0.025. T equals 0.050. T equals 0.075. T equals 0.100. T equals 0.125. Answers 2010, 10. 190. Figure 13 Kant. T equals 0.200. T equals 0.225. The second example is a ball falling in paratherm fluid. A ping-pong ball with a diameter of 3 cm, weld with glass beads with a density of 2,500 kilograms per meter cubed, and an average diameter of 250 microns was initially suspended by a thread statically in paratherm fluid with a density of 867.9 kilograms per meter cubed and a viscosity 0.31 Pascal sex contained in a 0.1 meter ID column mounted with a cylindrical ECVT sensor. The ball was let free fall with a zero initial velocity. The process of the falling ball in paratherm fluid is obtained by ECVT, and a snapshot of the ball in the liquid is illustrated in Figure 14. Figure 14. Snapshot of a ball falling in paratherm fluid by ECVT. Red and blue colors represent solids and fluid respectively. The vertical position of the center of the ball is plotted against time using three different methods: ECVT, E, computational fluid dynamics, CFD, O, and a high-speed camera, W, in Figure 15. The high-speed camera experiment was conducted with identical conditions to the ECVT experiment in a transparent column. A Phototron ASTCAM PCI high-speed CCB camera with 500 fps was used to capture the position of the ball. A CFD model using the fraction volume method was used to track the motion of the ball in the fluid. The method is based on the two-way coupling technique that uses a cubic mesh in Cartesian coordinates, 73. The particle size is about 15 times that of the mesh size. The velocity of each computational cell is represented by the volume-weighted average of the fluid velocity and particle velocity. The fractional step algorithm is employed in the solution procedure, in which a sensors 2010, 10, 190 has been implemented based on the CFD Lib code, which was originally developed by Los Alamos National Laboratory but has been extensively modified by FAN 74 to model various multi-phase problems. The position of the ball in Figure 15 verifies the accuracy of ECVT for tracking difference phase concentration, as the results from ECVT, the high-speed camera, and CFD were found to be very good agreement. Figure 15. Comparisons of measurements using high-speed camera, ECVT, and CFD for the relative position and time of a free-falling ball in the paratherm fluid. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, 0.05, 0.1, 0.15, 0.2, time, S, height, centimeters, high-speed camera, CFD, ECVT. Figure 16 illustrates a single bubble rising in a bubble column with paratherm fluid. A certain amount of air was first held in a cap at the bottom of the sensing domain. The cap was turned over and a single bubble formed above the cap and rose upward. The bubble kept its shape during the motion. Another example is the bubble bursting process at the bed surface in a gas-liquid-solid slurry bubble column, 71. Air, paratherm fluid, and alumina oxide-based particles with a mean diameter of 150 micron and a density of 1500 kilograms per meter cubed were used as the fluidizing gas, liquid phase, and solid phase, respectively. The solids loading in the slurry was 9.1 vol%. A superficial gas velocity of 0.2 meters per second was used in the slurry bubble column. The ECVT sensor was mounted near the bed surface area outside the column to image the bed surface in the ECVT sensing domain, as illustrated in Figure 17. Figure 18 depicts 3D images before and after a bubble bursting through the surface of the slurry bubble column. After bursting, more liquid and solids were pushed upwards to the freeboard and to the wall, and a cavity with high gas fraction was formed at the surface of the bed. Small film and jet droplets formed during the bubble bursting were not detected by ECVT due to the volume image resolution of 5 mm by 6 mm by 6 mm. Figure 16. Snapshots of a single bubble rising in a bubble column with paratherm fluid by ECVT. Answers 2010, 10, 191. Figure 16. ... T equals 0.15, T equals 0.20, T equals 0.25. Figure 17. Sketch of an ECVT sensor monitoring the bed surface in a slurry bubble column. Figure 18. Snapshots of bubble bursting at the surface of a slurry bubble column by ECVT. A. 3D image before bubble bursting. B. 3D image after bubble bursting. A. Bed surface, ECVT sensing region, slurry bubble column. Qussai 2010, 10, 191. Figure 18. B. Tomography measurements of complex geometries are rarely reported due to the obscure sensor design and the complexity of implementing image reconstruction. However, vessels with complex geometries are very common in engineering processes. Images of multi-phase flows in such vessels are desired in research and for industrial reactor designs. Here, three-dimensional ECVT imaging of solids flow in a 90-degree bend is the first to be reported, demonstrating the capability of ECVT sensors for imaging flows in vessels with complex geometries. The sensor configuration and a photo of the sensor are provided in Figure 7b and Figure 8a, respectively. The outlet of the bend is 45 degrees facing downward to the ground, and a plate was installed to block particles from falling. FCC particles, Group A, with a density of 1,400 kilograms per cubic meter and a mean diameter of 60 microns, were poured in the bended vessel. The sensor used here is similar to the one depicted in Figure 7b. After the plate was removed, FCC particles were discharged from the bended vessel by gravitational force. Figure 19 shows the dynamic images of the solid's concentration in the bend during the discharge process. Red and blue colors represent high and low FCC solids concentrations, respectively. Quantitative images from the ECVT bended sensor can be used to study the hydrodynamics of gas-solid flow in the elbow of solid pneumatic transport vessels and in the exit region of solid circulating fluidized beds. Figure 19. Snapshots of solids discharge in a 90-degree bend by ECVT. T 00000 T 00375. Answers 2010 10.
Sensors 2010-10. 191. Γρήκα γράμματα. έψιλον διαηλέκτρικος κανόνας, περιμή του βιπίατος διαστήματος sensing. Φι potential διαστήματος sensing referiation. Καταθέσεις. Κούνι, Ντάο, Levenspiel, Ο, Fluidization Engineering, δεύτερο έκδοχε, Butterworth Heinemann, Boston, Να, USA, 2091, σέλιδες 491. Φαν, L, S, Ζου, Σε, Principles of Gas Solid Flows, Cambridge University Press, New York, NY, USA, 1998, σέλιδες 557. Christensen, H.G. Scheffer, Tough, Granulation, A Review of Pharmaceutical Wet Granulation, Drug Develop Int. Farm, 1987, 12, 803-872. Cohen, J.S., Young, T. Se, Progress in Food Dehydration, Trends Food Science Tech, 1995, 6, 20-25. Dixit, R. Puthli, S. Fluidization Technologies, Aerodynamic Principles and Process Engineering, J. Parm Science, 2009, 3310 Κοσκός. Φαν, L.S. Gas Liquid Solid Fluidization Engineering, Butterworth, Boston, MA, USA, 1989, σέλιδες 763. Geldart, D. Kelsey, J.R. Use of Capacitance Probes in Gas Fluidized Beds, Powder Tech, 1966, 45-50. Yutani, N. Ho, T. Se, Fan, L. T. Wallawender, W.P. Song, J. Se, Statistical Study of the Grid Zone, Behavior in a Shallow Gas, Solid Fluidized Bed using a Mini Capacitance Probe, Chem. Eng. Sec, 1983-575-582. Kui, H. P. Chauki, J. Effects of temperature on local two-phase flow structure in bubbling and turbulent fluidized beds of FCC particles. Chem. Eng. Sec. 2004, 3413-3416. 10. Liu, J. Z. Grace, J. R. B. X. T. Novel Multifunctional Optical Fiber Probe, I. Development and Validation, AICHEJ, 2003, 41-15-16. 11. Liu, J. Z. Grace, J. R. B. X. T. Novel Multifunctional Optical Fiber Probe, II High Density CF Measurements, AICHEJ, 2003, 41-42. 12. Kang, W.K. Sutherland, J.P. Osberg, G.L. Pressure Fluctuations in a Fluidized Bed with and Without Screen Cylindrical Packings, Int. Eng. Hem. Fund, 1969, 6-499. 13. Fan, L.T. Ho, T. Hiraoka, S. Wallawender, W.P. Pressure Fluctuations in a Fluidized Bed, AICHEJ, 1927-389. 14. Xi, Iota, The, Geldart, D. The Response Time of Pressure Probes, Powder Tech, 1990-90-141-151. 15. Peters, M.H. Fan, L.S. Sweeney, Tel L. Study of Particle Ejections in the Freeboard region of Fan, Fluidized Bed with an Image Carrying Probe, Chem. Eng. Psek, 1983-481-485. 16. Du, B. Warsito, Wei, Fan, L.S. ECT Studies of the Choking Phenomenon in a Gas Solid Circular Fluidized Bed, AICHEJ, 2004, 1386-1406. 17. Plaskowski, A. Beck, M.S. Process Tomography, Prezem, Chem, 1988-67-104-106. 18. Wang, S.M. Xi, Xe, J.A. Plaskowski, A. Torn, R. Williams, R. A. Beck, M.S. Process Tomography for Identification, Design and Measurement in Industrial Systems, Powder Tech, 1992-85-82. 10.
Savelsberg on DE, Demko DE, Blumich B, Staff S. Particle motion in gas fluidized granules, systems by pulsed field gradient nuclear magnetic resonance. Phys. Rev. 2002 6020301-02301. P. Fennel, P.S., Davidson, J.F., Dennis, J.S., Gladden, L.F., Hayhurst, A.N., Mantle, M.D., Mueller, C.R., Reese, S.A., Scott, S.A., Setterman, A.J. A study of the mixing of solids in gas fluidized beds using ultrafast MRI. Chem. N. Sci. 2005, 60, 2085-2088. 1. Wang, R.P., Rosen, M., C. and E., Candela, D., Mayer, R.W., Walsworth, R.L. Study of gas fluidization dynamics with laser polarized XE129. J. Mag. Resonance. Imaging 2005, 23, 203-207. 2. Holland, D.J., Marashdeh, Q., Mueller, C., Wang, F., Dennis, J.S., Fan, L., S., Gladden, L. Comparison of ECVT and MR measurements of voidage in a gas fluidized bed. Ind in Chem. Sci. 2009, 48, 172-181. 3. Dechsiri, C., Gion, A., Von de Will, F., Dealing, H.G., Pans, A.M.J., Hoffman, A. Positron emission tomography applied to fluidization engineering. Ken, J., Chem, N., Sci. 2005, 83, 88-96. 4. Dechsiri, C., Von de Zwaan, E., Daling, H.G., Hoffman, A. Dispersion of particle pulses in fluidized beds measured by positron emission tomography. AICHE-J, 2005, 51, 791. 5. Simons, S.J.R., Imaging Techniques for Fluidized Bed Systems, a review. Chem. N. J. B. N. J. 1995, 56, 83-93. 6. Rowe, P.N., Partridge, B., An X-ray Study of Bubbles in Fluidized Beds. Trans. N. Chem. N. Com. N. 1965, 43, 157-161. 7. Rowe, P.N., Partridge, B.A., An X-ray Study of Bubbles in Fluidized Beds. Chem. N. R.D. 1997, 75, S116, S134. 8. Clough, D.E., Weimer, A.W., Time-Dependent Behavior of Bubble Volume in Fluidized Bed. In Chem. N. Fund, 1985, 24-35. 9. Wang, Z.C., Afakan, A., Nandakumar, K., Chuang, K., Porosity Distribution in Random Packed Columns by Gamma Ray Tomography. Chem. N. P. 2001, 40, 209-219. 10. Patel, A.K., Wajay, S.S., Thorat, B.N., Mujumdar, A.S. Tomographic Diagnosis of Gas Maldistribution in Gas-Solid Fluidized Beds. Powder Tech, 2008, 185-239-250. 11. Williams, R.A., Beck, M.S., Process Tomography, Principles, Techniques, and Applications. Butterworth, Heinemann, Boston, USA, 1995, pp. 581-588. 12. Shi, C.G., Huang, S.M., Hoyle, B.S., Thorne, R., Len, C., Snowden, D., Beck, M.S. Electric capacitance tomography for flow imaging. System model for development of image reconstruction algorithms and design of primary sensors. EE Proceedings-G, Circuits, Device, Sys, 1992, 139-89-98. 13. Wang, W.Q., Peng, L.H. Image reconstruction algorithms for electrical capacitance tomography. Measure, Sci, Tech, 2003, 14, R1.
14. Warsito, W, Fan, LS. Neural network-based multi-criterion optimization image reconstruction technique for imaging 2- and 3-phase flow systems using electrical capacitance tomography. Measure Psi Tech 2001 2198-2110. 15. Do B Warsito W Fan LS. Bed non-homogeneity in turbulent gas-solid fluidization. AICHE J 2003 49 1109-1160.
10. Warsito 2010 1916. Marashdeh Q. Warsito W. Fan LS. Texera FL. Nonlinear forward problem solution for electrical capacitance tomography using feed-forward neural network. IEE Sensors J 2006 441-449. 7. Wang F. Marashdeh Q. Fan LS. Williams RA. Electrical capacitance, electrical resistance, and position emission tomography techniques and their applications in multi-phase flow systems. In Advances in Chemical Engineering, Volume 37, Characterization of Flow, Particles, and Interfaces. Lee, J.H., ed. Academic Press, Amsterdam, the Netherlands, 2009, pp. 179-222. 8. Warsito, W. Fan, L.S. Measurement of real-time flow structures in gas-liquid and gas-liquid-solid flow systems using electrical capacitance tomography. Chem and C. 2001, 56, 6455-6462. 9. Warsito, W. Fan, L.S. Neural Network Multi-Criteria Optimization Image Reconstruction Technique. NN-MORT for linear and nonlinear process tomography. Chem Eng Process 2003 42 663-6674. 0. Warsito W. Fan LS. ECT imaging of 3-phase fluidized bed based on 3-phase capacitance model. Chem Eng Psi 2003 58 823-832. 1. Warsito W. Fan LS. Dynamics of spiral bubble plume motion in the entrance region of bubble columns and 3-phase fluidized beds using ECT. Chem and Psi 2005 6063-60684. 2. Warsito W. Marashdeh Q. Fan LS. Electrical capacitance volume tomography ECVT. IEE Sensors J 2007 7 525-535. 3. Fashing G.E. Smith N.S. High-Resolution Capacitance Imaging System, U.S. Department of Energy, 1983, 37 DOE/MET 88408. 4. Fashing G.E. Smith N.S. A capacitive system for 3-dimensional imaging of fluidized bed. RSI 1990 62 2243-2251. 5. XCG Reineck N. Beck M. Muse D. Williams R.A. Electrical tomography techniques for process engineering applications. Chem Eng B. EBJ 1995 56 127-133. 6. Yang W.Q. Beck M. Byers A. Electrical capacitance tomography from design to applications. Measurement control 1995 28 261-266. 7. Beck M. Byers T. Diakovsky T. Waterfall R. Hay R. Wang S.J. Yang W.Q. Principles and Industrial Applications of Electrical Capacitance Tomography. Measurement Control 1997 33 190-190. 8. Diakovsky T. E.W. Shih C.G. Williams R.A. Application of capacitance tomography to gas-solid flows. Chem Eng C. 1997 52 2099-2110. 9. Bennett, M.A., West, R.M., Luke, S.P., Williams, R.A. The investigation of bubble column and foam processes using electrical capacitance tomography. Mineral Engineering, 2002, 15, 225. 0. Chaplin, G., Pugsley, T., Vanderlee, L., Contaz, A., Winters, C. The dynamic calibration of an electrical capacitance tomography sensor applied to the fluidized bed drying of pharmaceutical granule. Measure Science, Tech, 2005, 16, 1281. 1. Ostrovsky, K.L., Luke, S.P., Bennett, M.A., Williams, R.A. Application of capacitance electric tomography for online and offline analysis of flow pattern and horizontal pipeline.
Sensors 2010, 10. 191. Ostrovsky, K.L., Luke, S.P., Williams, R.A. Simulation of the performance of electric capacitance tomography for measurement of dense phase pneumatic conveying. Chem N 1997, 68, 197 to 205. 3. Du, B, Warsito, W, Fan, L.S. ECT studies of gas-solid fluidized beds of different diameter. End.eng.chem.res, 2005, 44, 5020-5030. 4. Du, B, Warsito, W, Fan, L.S. Imaging the choking transition in gas-solid risers using electrical capacitance tomography. End.eng.chem.res, 2006, 45, 5384-5395. 5. Du, B, Warsito, W, Fan, L.S. Behavior of the dense phase transportation regime in circulating fluidized bed. End.eng.chem.res, 2006, 45, 3741-3751. 6. Fan, L.S., Warsito, W, D. Electrical capacitance tomography imaging of gas-solid and gas-liquid-solid fluidized bed systems. J.Viz, 2004, 7, 5. 7. Marashdeh, Q, Warsito, W, Fan, L.S. Texira, F.L. A nonlinear image reconstruction technique for ECT using a combined neural network approach. Mez.sci.tech, 2006, 1, 2097-2103. 8. U, G, Ju, C, Du, B, Fan, L.S. Heterogeneous structure in gas-solid riser flows, AICHE, 2008, 54, 1459-1469. 9. Wajman, R, Banasiak, R, Mazorkiev, L, Dyakovsky, T, Sankovsky, D. Spatial imaging with 3D capacitance measurements. Mez.sci.tech, 2006, 17, 2113-2118. 10. Soleimani, M, Mitchell, C, N, Banasiak, R, Wajman, R, Adler, A. Four-dimensional electric capacitance tomography imaging using experimental data. Prague.electromagnetics.res, 2009, 91, 171-186. 11. Warsito, W, Marashdeh, Q, Fan, L.S. Some comments on spatial imaging with 3D capacitance measurements. Mez.sci.tech, 2007, 18, 3665-3667. 12. Wang, F, Marashdeh, Q, Warsito, W.F. Imaging gas-solid jet penetration in a gas-solid fluidized bed using electrical capacitance volume tomography in Proceedings of AICHE Annual Meeting, Philadelphia, PA, USA, 1621 November 2008. 3. Tech for Imaging. Available online, www.techforimaging.com, accessed on 6 February 2010. 4. Williams, A, Wang, M, LLC, Porkashanian, M, Electrical Capacitance Tomography for High-Temperature Flames, in Infu B, Villamora, Portugal, March 25, 28, 2008. 5. Marashdeh, Q, Fan, LS, Du, Warsito, W, Electrical Capacitance Tomography, A Perspective, ind.eng.chem.res, 2008, 47, 3708-3719. 6.
Wang F, U, Z, Marashdeh Q, Fan LS, horizontal gas and gas solid jet penetration in a gas solid fluidized bed, Chem.Eng.Sci 1971 26 923 to 925. 7. Y7 5-year seed fund awards available online http://www.nasa.gov/pdef 368044main-09 seed fund awards accessed on 5 February 2010. 8. Peffer, R, Zakin, P, A.H. Preface to the LS Fan Festive Tech, ind.eng.chem.res, 2008, 48, 2-3. 9. Marashdeh Q, Wang F, Fan LS, velocity measurement of multi-phase flow based on electrical capacitance volume tomography. In Sensors, 2007, IEEE, Atlanta, GA, USA, October 28, 31, 2007, pages 1017-1019.
1010, Marashdeh, Q, Wang, F, Warsito, W, Fan, LS. 3D velocity profiles of multi-phase flow systems using electrical capacitance volume tomography. In proceedings of 3rd International Workshop on Process Tomography, IWPT3, Tokyo, Japan, April 17, 19, 2009. 1. Wang, F, Marashdeh, Q, Warsito, W, Fan, LS. 3-dimensional velocimetry in a fluidized bed system using electrical capacitance volume tomography. In 8th World Congress, Chemical Engineering, and 9th International Conference on Gas Liquid and Gas Liquid Solid Reactor Engineering. Montreal, QC, Canada, August 23, 27. 2. Wang, F, Marashdeh, Q, Warsito, W, Fan, LS. Validation of 3D ECVT velocimetry in multi-phase flow systems. In proceedings of AICHE Annual Meeting, Nashville, TN, USA, November 8, 13, 2009. 3. Kajishima, T, Takiguchi, S, Interaction between particle clusters and particle-induced turbulence. Int.J, Heat, Fluid Flow, 2002, 23, 639, 646. 4. Fan, LS. Advances in gas-liquid-solid fluidization. In Fluidization-11, Arena, U, Chiron, Salatino, P, eds. Engineering Conferences International Press, New York, NY, USA. 2004, pp. 1-20. 2010 by the authors. Licensee Molecular Diversity Preservation International, Basel, Switzerland. This article is an open access article distributed under the terms and conditions of the Creative Commons Attribution License, http://creativecommons.org.licenses/by/3.0.